Yeah, so this is one very important feature. Now, another important feature about liquid reacting to pressure is that the liquid will always flow in a way to equalize the pressure. Now, what do I mean by this? Uh, Imagine if you have a bucket that is like that, and when you pour water in, will the water level becomes like that? No, right? If you pour water into an irregular shaped chamber, somehow the liquid level will spread out. And that is because your surrounding pressure, atmospheric pressure, will act equally on every surface and will push the water level down. It will spread out nicely. Now, what scientists see in this is that they make use of this and come up with this thing called a barometer. So let me explain to you how this barometer works, and it is very important that you learn this because this will also introduce to you one more unit for your pressure. So I want you to imagine now that I have a bucket of mercury. So if I pour mercury in, the mercury will just fill up the bucket, right? Nicely and flat. Agree? Now what I'm going to do is that I'm going to insert a tube with both ends open into the mercury reservoir. Now when I do that, what would happen is that, well, the mercury will go into the tube and fill it up. Now because the tube is open on the top, basically everywhere on the surface will still experience atmospheric pressure, and so it will be flat, right? Now what if now what I'm going to do is that I am going to seal up one end of this tube. So it is sealed, only this side is open up. Now when I do that, then okay, the thing will be still going in. But what if now after I seal it up, I try to suck out the air that is trapped within the mercury, within this tube. Now when I suck out the air, what happens is that the mass of the air inside this tube will reduce, and of course the number of particles per unit volume will drop, collision frequency between the molecule and the wall will drop. So as a result, the pressure that is inside this tube will be almost zero if now I remove the air. So what happens is that this pressure in the tube will be almost zero. Now something interesting will happen is that while I do that, the pressure outside is actually the P atmosphere, which is a big value, about 100,000 PA. Now because fluid can move, so what happens if down here I am pressing down hard with the atmospheric pressure, and down here inside I have almost no pressure and I have empty space? How would you think the mercury will react? The mercury will start going into the tube and building up itself, right? But will this mercury liquid rise infinitely? Well, it depends, because as the mercury column rise over here, the mercury down here will get heavier and heavier, and what is supporting this mercury column is the pressure outside that is pushing the mercury into the tube. So basically this column height is an indication to how much pressure that is on the outside here. So what happened is that we have built this simple device whereby I basically have a reservoir of mercury or any fluid, and I put a tube like that, and then I fill this thing up, this mercury, I fill this reservoir up with mercury, and of course I have to make sure that here I vacuum it. Basically I remove all the air that is inside here. Now when that happens, the mercury column will start going into the tube because on the outside the atmospheric pressure is pushing the liquid into the tube, right? And it will push them into the tube until the liquid column that is in the tube is just nice being supported by down here, the atmospheric pressure. Meaning to say, if my atmospheric pressure is very high, my column that can go into the tube will be taller or shorter? It will be taller, right? So actually we actually can make use of an equipment like that. If I see that this mercury column height is tall, then we can conclude that the surrounding pressure must be high. So we use this instrument to actually measure our surrounding pressure. So this is a concept. So how do we measure exactly? How do we get a number? Well, we say that the pressure here, this red dot, and the pressure here inside the tube has to be the same. So we usually call this P1 and this is P2. So if I look at this, P1 is equals to P2, right? P1 is being pressed down by the atmospheric pressure. P2 is being pressed down by vacuum. Well, vacuum has no air particle inside, so no pressure. That means P2 is the pressure experienced by P2 is solely given by this liquid column. And we have learned how do we calculate the pressure exerted by a liquid column, right? We use rho GH. So when we do that, we actually find out that, oh, this rho GH and this atmospheric pressure will produce the same pressure. Now, it is sometimes, if I have to make use of this and then I have to multiply density of the fluid and multiply by the height and everything to give me a reading in Pascal, it is quite troublesome because we have to use calculator and all, right? So what the scientists do is that they use this equipment and they measure the pressure in terms of cm Hg. Now what is cm Hg? Basically they just put a ruler over here and basically they measure the height. So if under atmospheric pressure, most likely it will support a mercury column that is of 76 mm Hg. Okay, so it will support a column of 7.6 cm. So we say that, oh, okay, the atmospheric pressure is basically 76 cm Hg. That's all. Okay, so what is Hg? Hg is the fluid that is being used, and Hg is the chemical symbol for mercury. So most of the time your barometer, they make use of mercury, and then depending on the surrounding pressure, it will support a certain column of mercury over here, and basically we measure the atmospheric pressure in terms of how tall the liquid column is. So this 76 cm Hg is basically telling you that, oh, the atmospheric pressure can support 76 cm height of mercury column. So for example, if you decided to climb a very high mountain, so when you climb a very high mountain, when you reach the top, you're actually under a very thin layer of atmosphere compared to when you are at the bottom where you are under a deep layer of air. And if you bring a barometer up here, you will find that the mercury column that can be supported will be way less than 76 cm Hg. Now you may ask me, teacher, then how to convert cm Hg to Pascal? Well, it's the same. If you know that you are under 76 cm height of mercury, then you just take mercury's density times the G, which is 10, and then multiply by 0.76. So just remember your H here should be in meter. Yeah. So now that is the basic concept of a barometer, and of course, the other thing you need to recall is that, oh, okay, now we know that fluid will flow to actually equalize the pressure, and pressure can be measured by cm Hg. So now can you take out your worksheet 7.0, and we are going to consolidate our learning in the worksheet. Okay, principle of a barometer. So for example, now I have this barometer and I name MNOPQ for 5 points, and I want to ask you what is the pressure there. So if now I ask you what is the pressure at point N, well, above point N is vacuum, right? Basically vacuum is nothing. So if I want to find pressure of N, it is equals to 0 lor. Yeah, can. How about pressure of M, O, and P? Well, since they are on the same liquid level, they will be the same. Yeah, so let's take a look at the question here. Part A. Hence fill in the blank. When the atmospheric pressure is high, the height of the liquid column will be high lor. If now the atmospheric pressure is dropping, what will happen? It will decrease. It will become lesser. What is meant by atmospheric pressure of 760 mm Hg? Well, it means that the atmospheric pressure can support the weight of a 760 mm mercury column acting over an area. Simple as that. Yeah. Or you can say that the atmospheric pressure is the same as the pressure under a mercury column that is 76 cm or 760 mm. So if you like that, you can also do that. You can say that the P atmospheric pressure is the same as the pressure exerted by a mercury column of 760 mm height. Okay, so how do I convert? Well, this is the conversion part. So P is equals to rho GH, right? So how much is 7720 mmHg? Well, I do not know, but I know that it is the same as, so this particular pressure is the same as the pressure exerted by a mercury column that is 720 mm high, right? So it's the same thing. Rho GH, I would have, so this is the pressure that I'm talking about. It is a column that is 720 mm tall. So therefore I will put in my density, then my gravity, and finally my height in terms of meter. So once I do that, I will be able to get the answer, and it has to be 2SF. Yeah. Okay, this one is to check whether you are a strong believer that P is equals to rho GH. So down here what happened is that the surrounding pressure, which is here, your P atmosphere, can now support a column of 1 square, 2 square, 3 square, right? It will support 3 units. So since it is the same atmospheric pressure, that means down here the pressure can support 1 square, 2 square, 3 square. It will support 3 units. So they are the same. Okay. So let's carry on checking on 8, 9, and 10. Basically, these last 3 questions, right, I really would want you to try it on your own first before you actually look at the answer.